Hey, so welcome back, and this is another daily Go problem. So today it's called convert binary search tree to greater tree. And so basically you're just given a binary search tree here. And just to recap on this data structure, it means binary so that each node is going to have at most 2 children. But then it's a search tree because, well, it's ordered in a way so that, say if you go in order traversal, you'll start at this node here, and you can kind of see the way that you traverse it, it's always going to be like an increasing node values. And this kind of binary search tree structure is great because it essentially allows you to find any value in log n time. And well, that's because, well, say if you start at this node 4, your search space is going to be divided by 2 each time, and that basically results in a log n time traversal. And that's because, well, you could just say at every node, okay, is the value that I'm looking for, say it's 8 in this case, is it greater than or less than 4? If it's greater than, we go to the right. Now we're at 6, we say, okay, is it greater or less than? It's greater, so we go to the right. Once again, is it greater than 7? Yep, we go to the right, and then we get to 8. So basically, this binary search tree is allowing us to kind of find our values that we're searching for very quickly. Now, what we want to do, and that kind of just summarized the data structure that we're working with, is we want to create a greater tree. And so all that we're going to do is we're going to update these values to a new one that's kind of defined by this greater tree definition. And so what that is essentially you're going to be adding all the values in the tree that are greater than the current value. And so one simple implementation of that is, okay, what values in this entire tree is greater than 7? Well, it's 8. And so you're basically just adding 8 to 7 to get 15. And then basically you're rewriting this value 7 as 15 here. So you can see in the output, 7 has become 15. So basically delete that kind of 7 value and replace it with 15. And so the reason why a binary search tree is so helpful, and they kind of simplify it by already making it a binary search tree, and that's because, well, everything to the left of the node 4 is going to be less than 4, and everything to the right of this node is going to be greater than this node's value. And so because this node's value is 4 here, we can see, okay, the left side has 0, 1, 2, 3, well, that's less than 4, and everything to the right, 5, 6, 7, 8 is greater than it. Another example would be, okay, at 6, I want to change to the pen. At 6, the left-hand side, well, that's 5 and 4 and 1, 2, 3. Those are all less than 6, and everything to the right here, you can see it's greater than 6. And so the reason why this is useful is at every step we can see here that, okay, when we're at 7, we just want to consider the values on the right of it and basically add it all to the current node and then replace that node's value. And so say when we're at 5 here, we once again split it in half, left, right, and we want to add all the values on the right-hand side. Okay, so when I was solving this problem, I thought of, okay, do we want to use a pre-order traversal, in-order traversal, post-order? I was kind of thinking of all the depth first search ways of doing it. And the one that came to mind that closely resembled this problem that we're trying to solve is in-order traversal, which is basically left, current, right. And that's because we're kind of going down to the bottom, evaluating the current node, and then going up, and then going down a different path. But really, we're not going left, current, right. I realized pretty quickly we want to go right, current, then left. And that's because we want to start at this node, but then go all the way down to 8, then go to 7, then go to 6, then go to 5, and then go to 4 and so forth. So we're kind of bringing it from this like right side to the left side each time. And that allows us to propagate the answers up, rewrite the node's value, and then push on to the next node on the left-hand side. Now, if that doesn't quite make sense, I think the code is pretty self-explanatory, so let's take a peek at it. So essentially we're given a method here called convert binary search tree. And because we want to be kind of maintaining the total value that we're propagating up and rewriting the nodes, we don't really have enough parameters here. So we decided to use a helper function, and just for simplicity, we'll just call it helper. But then we're also specifying like the current running value or the total value or whatever you want to call it. But it's initially just going to be 0 because we haven't kind of appended or kept adding and incrementing it yet. So let's go ahead and define this. So we have our helper function, and we're going to have the current node, and then we're going to have the total. And so typically the first thing that you want to check is, okay, do we actually have a node here? And otherwise, let's just return the current total, and we just will ignore it. So otherwise, we're basically just returning the current total. But if there is a node, let's go ahead and process it. Now, like I said, we want to go down the right node. Then we want to evaluate the current node. And then we want to go down the left node. All right, and so to go down the right node, that's as simple as, well, we want to call our helper function again, but now go down the right path and kind of push this total on down that train. All right, and so from here, then what we're going to want to do is, okay, and we want to evaluate our left node. It's just going to be simple as, well, let's go down the left direction. And so now this is where it comes to, okay, but how do we actually start incrementing this value? Because right now we're just traversing this tree in the order that we want, but we're not updating anything. And so that's where this comes in, where we start evaluating the current node. And so we're essentially just going to be appending to the total the current node's value, so node.val. And so this is updating it so that now we've appended the current node. And so then we're going to want to rewrite the node's value as that total. And so what this is hopefully going to look like is, say we go here, we start at 4, we keep going right until we hit the bottom, then we just kind of return 0 upwards. We then go down right again, then we return 0 upwards because this total was initially set to 0. But then we see, okay, let's add the node's value to the total, which is 8, and then we're going to be propagating 8 upwards to 7, and then 7 plus 8 is 15, so then this 15 gets propagated upwards, and so forth. Now, the one catch here is we're not actually propagating that value upwards yet. We're only just kind of appending the current node's value to this and then rewriting it. But if we want to be pushing that upwards, what we need to do is so that when we go down the right path, that we're updating our total. And when we're going down the left path, we're updating our total. And so this is just allowing us so that, yes, this is how we actually upgrade or include the current node's value. But if we want to actually push it up to the next level, we got to make sure that, okay, we are returning that total. And so we want to reset it here, and then also we want to return it here. But you can see for simplicity, we don't really need this else, so we can just push this down a level, and it does the exact same thing. Okay, so let's go ahead and run that. Oh, looks like we have a problem. Let's take a peek. So we're outputting nothing right now, and that's because, well, we actually have to return something. So here, we want to return our root. And success. And looks good. So for time complexity, well, naturally this is going to be running in kind of O of n time, where n is the number of nodes in this tree. And that's because, well, if we do this kind of right, current, left, we're going to visit every single tree or every single node in our tree. But yeah, I hope that helped. I hope it explained it a little bit. Typically you want to think of, okay, if I'm going to be exploring every node, I probably want to use breadth first search. And then with that, okay, how am I going to traverse this node? Well, there's kind of 3 main types: in order, post order, and pre-order. Of those 3, I kind of selected the in order way. And then I realized, okay, but I don't really want to do left, current, right. Let's actually go right, current, then left. So I kind of just swapped these 2. And once you know that, it's just as simple as, okay, I just need to modify what I'm doing when I'm evaluating the current node, and then the rest is the same. But yeah, I hope that helped, and good luck with the rest of your algorithms. Thanks for watching.